Okay, so we're going to start to discuss titration curves. When we did acids and bases first semester, it was more about concentration, molarity, measuring volumes, using your burettes. But now that we're talking more on the pH side of acids and bases, like we've discussed the fact that if you add a strong acid and a strong base, you get a neutral salt. Okay, so the pH would be 7. If you add a strong acid and a weak base, then your resulting salt solution is actually going to be acidic. And because it's acidic, its pH would be less than 7. So we've been talking a lot more about pH. And there is an alternative way to do a titration. Instead of actually measuring the volume of the base added to the acid using the burette and whatnot, you can actually stick a pH meter into your Erlenmeyer flask and measure the pH the whole time. And if you measure the pH the whole time, you can graph those pHs, and you can tell a lot of things from the graph, actually more than we can tell just from our calculations of stoichiometry that we did over the weekend. So that's actually pretty useful. Before we get going, though, let's start by looking at the definition of equivalence point. Equivalence point is defined as the point where the acid and the base have stoichiometrically reacted to neutralize each other. Now be careful of that word neutralize. Neutralize means to form neutral water, but the salt that forms may make the solution either acidic or basic or neutral, depending on what combination of strong acids and strong bases you have. You might also write down in your notes the definition of endpoint. Endpoint is the point where the indicator changes color. Okay, endpoint is the point where the indicator changes color. To have a successful titration, you would want your equivalence point and your endpoint to match up. But honestly, if you're graphing titration curves, you don't even have to have an indicator because the curve is going to do all the work for you. You are going to intentionally overshoot the endpoint just to graph what you need to graph. So to be honest, you don't really need an indicator with titration curves. All right, this is an example of a titration curve. Notice our axes here are pH compared to the volume of the base being added. Okay, so what this is the pH of here is the acid that's inside the flask. Remember, we always put our acid inside of our flask. So notice the pH starts very low, very acidic. As you add the base, you see that it slowly starts to go up a little, and then boom, all of a sudden it hits this point, and within hardly any volume at all, that one drop that we've seen so many times, it jumps. All the way from, this one goes from a pH of about 3, all the way up to a pH of 10 instantly, okay, literally with one drop. And that will happen with every titration curve. You will have that huge jump. Right smack dab in the middle of that jump is where the equivalence point pH is. So on this one, if you look, the pH at the equivalence point is equal to 7, which makes sense because this one told us this was the mixture of a strong acid and a strong base. And we know a strong acid and a strong base make for a neutral salt. So that would be logical. Excuse me, that would be logical. And so even if you don't have a strong acid and strong base, still the look of the curve is going to be very similar. It's going to start off relatively flat, jump up, and then go flat again. This right here, this whole area from here on is overshooting the endpoint. So we never have actually gone this far in a titration. We usually stop at the equivalence point. But when we're graphing, it's fine to keep going because we can easily find the equivalence point. Again, it's just halfway up the big jump. So this one's strong acid, strong base. This one is a weak acid and strong base. So again, remember the acid is being represented by the pH over here. So notice this time the pH starts higher because it's a weak acid. That is logical that the pH would be higher. And it finishes as a strong base. So you can see up here that we are up at a very strong pH in terms of bases, a very high pH in terms of it being basic. To be able to figure out the equivalence point on this, again, we're simply going to go halfway between the jump. So there's the jump. Halfway would be about there. So we would follow that over. And maybe we would say on this one that it was pH of 9.5, say. We'd need a better graph to do this better. But again, this is an estimate anyway. So this point right here is the equivalence point. So just by graphing it, we can figure out the equivalence point. This pH is logical because that pH shows that the resulting solution is basic. When we react an weak acid with a strong base, we get a basic salt. And that salt is going to be dissolved in that water, therefore making that water basic. So you can tell by looking at the graphs what kind of combination you had. Another graph we have is this one. This one is for a polyprotic acid. If you remember, polyprotic acid means more than one hydrogen. So something like carbonic acid is polyprotic. Phosphoric acid is polyprotic. So the reason why we knew this one was polyprotic is you see there's a jump here. That would be the loss of the first hydrogen. Then there's a jump here. That would be the loss of the second hydrogen. So this graph might be the graph for carbonic acid. Okay, don't worry about any of these numbers I have up on mine. I think I got rid of them on yours. Really what we're looking at is the equivalence point. So for the first hydrogen loss, it happened at a pH equal to 6. The second hydrogen loss happened at a pH equal to 12, because remember, those hydrogens come off one at a time. Now I do want to go back, we'll use this graph as our example to show you one other thing. This region right here, you have this flattened region right before the equivalence point. What that right there is called the buffering region. Okay, the buffering region. And the reason why it's called a buffering region is because your solution is acting like a buffer during that. And we know a buffer means that it's resisting changes in pH. And if you think about it, it makes sense, because at that point, you are going to still have acid left, but you are also going to have some salt in there as well that has a conjugate. So it's going to act as that buffer, that ability. We just talked about the ability for acids and bases to be neutralized because of there being an acidic portion and a basic portion, and that will happen. Now a strong acid, strong base, it's not as pronounced because it's hard to get that good buffer with a strong acid, strong base. But again, you can see it happening here. This is going to be your buffering region. Okay, and then we can see it on the polyprotics too. It's a little more slanted on these ones because of the proportion of the graph, but it's still that region right before the equivalence point jump. So if you're ever asked a question that says, where's the buffering region of this graph, it's going to be always right before the big jump that you have. Okay, just wanted to point that out. So this part's just saying that if you look at the start of the curve, it'll tell you whether or not you're starting with a strong acid or a weak acid. These are real general, but the pH for a strong acid is usually less than 2, and for a weak acid usually greater than 2, obviously less than 7, and then the same way on the other one. So if you think about that, it can help you actually decipher what you're dealing with in a graph. And then for the equivalence point, just go halfway up the jump. If the pH halfway up the jump is less than 7, it's acidic, equal to 7, it's neutral, or greater than 7, it will be basic. So we can look at a graph and tell a lot about what was titrated. On this one, if you take a look, what we're highlighting here is the difference between this jump and this jump. You notice the jump on the strong acid, this one here is strong acid, strong base. And this one is, we're starting pretty high, so this must be a weak acid, and we end very high at pH, so that's going to be a strong base. In strong acid, strong base titrations, you're going to get a much larger jump, a much clearer equivalence point than in a weak acid, strong base. Okay, and again, it comes from complete dissociation. If you have complete and complete, it's pretty straightforward as to when all the neutralization occurs. So if you're ever asked, you know, the difference between these two, the strong acid, strong base will have a larger vertical jump. So just another fact off titration curves. Another one is that the stronger your acid is, the larger Ka will be. Think about what that means. We know that a bigger K value means more product has formed. So in terms of acid, that means more has dissociated. So since more is dissociated, it's stronger. Strength is based on the amount of dissociation. So you can see down here, for the strong acid, the curve has a huge big jump, and then it tapers off. And as these numbers get weaker and weaker and weaker and weaker, this one being the weakest, you can see that the jump is not as pronounced. This graph right here would be really hard to interpret your equivalence point off of because that acid is so weak. So titration curves work better the stronger the acid is, because you get a more pronounced answer, I guess. Okay, yeah. And then this note here is just saying that as it gets weaker, the equivalence point is going to be higher, because the weaker it is, the closer that pH is going to be to 7. And this is actually the last weak acid here. Nope, actually, nope, that one's basic. Sorry, I'm not looking at the right thing. Okay, weak base, weak base, weak base. This one starts acidic. Oh no, I am looking at the right thing. Just pretend like I didn't say anything. Thank you. All right, so this one starts at 4. This one starts at 2.5, almost 3. This one starts under. So those ones are all acids. So is that one, and so is that one. They are all starting as acids. Yeah, but their equivalence points with their base end up being higher because you're mixing an acid and a base. All right. Last thing, indicators. When we did titrations before, I always picked your indicator for you. We usually use phenolphthalein. It's a very good indicator, but I want to show you how you decide what indicator is appropriate to use. I'm going to flip back to our strong, here we can use this one, strong acid, strong base curve. So notice the jump starts at, we said, about 3 and ends at 10. So as long as we find an indicator that will change color somewhere in between 3 and 10, then it will tell us the equivalence point. So you go back and you look at this table. Yours is black and white, so it's not as pretty as mine. Mine actually shows you the colors. We want an indicator that's going to change somewhere in between 3 and 10. Let me use a different color here. So what I can do is I can draw a line across here. So anything that changes color in between this region here is an acceptable indicator. I just need the indicator to change color between a pH of 3 and 10. So you can see that methyl violet would not be a good one to use because it's blue the whole time. This one changes right about here, so that one would be acceptable. And I don't think you can read the words on your paper. That's fine. It's just looking at them. This one would be acceptable. This one changes here. That's acceptable. This one changes here. That would be acceptable. This one here, acceptable. This one here, acceptable. Here, acceptable. Here, acceptable. There's phenolphthalein. This one right here is phenolphthalein that you're used to. It changes in that range, which is why we've often used it. This one wouldn't be a good idea because it's clear the whole time, and this one would not be a good idea because it's yellow the whole time. So as long as you find an indicator that changes color in the appropriate range that you're looking for, then you'll be fine. A strong acid and strong base gets lots and lots of options. Okay, you have lots of options for those because the pH changes so drastically. Now on the AP test or on a test question, they're not going to give you this table of all these indicators. They're going to just tell you phenolphthalein changes pH around 8.8, okay, or changes color at a pH around 8.8. So you would say, well, I need it to change between 3 and 10, and 8.8 is between 3 and 10, so therefore that must be my pH, or the appropriate indicator to use for that pH change. Let's look at one more. This one, we'll do this weak acid, strong base. So it changed just above 8 and about 11.5. So somewhere between 8 and 11.5 I need it to change. So I'll erase this because I have a much smaller acceptable range for this one. So we'll go to about 8. Oops. 8 and 11.5. That was a horrible line. Okay, so this one's not good. This one's okay. Not good. 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 Phenolphthalein should be fine. This one should be fine. And this one, getting close. Might not be a great idea. I would use one of the other ones, but a possibility. Okay, so you definitely want to find one that falls within that range. Okay, now those are pretty much the types of things they're going to ask you about: indicator choice, what the equivalence point is, where the buffering region is, that type of thing. If you notice back on your front side of your notes, if you'll flip back to the front, there was also one other point listed on there that I want to make sure that you see. Go to this one. Just get rid of that. Okay, so if you go and take a look on your paper at about halfway in between Actually, we don't want to do it on this one because it's a strong acid. We want it on this one. Okay, halfway between the beginning and where your jump is, okay, that point right there is where the pH will equal the pKa. We'll discuss why that is a little bit later, but that's another question that they'll ask. You can actually figure out your Ka value from this table, because if this pH right here is 7, then that means your pKa is 7, and then you can take that pKa of 7, that's not really 7, sorry, I'm doing bad graphing, maybe 6.7, let's go with. You can take that pKa of 6.7 and figure out what the Ka is from it. So you can actually get so much mathematical information off of one of these graphs. So what you need to be able to do is find the equivalence point. You need to be able to find the pH and the pKa at this point right here, halfway between, okay, right here, this one. You need to be able to do that. You need to be able to locate buffering region. You need to be able to tell if it was a strong acid that you started with or a strong base that you ended with. You need to be able to determine equivalence point. What else? Indicators, figure out what your indicator is. Your homework is a bunch of AP questions, actually. So you're going to get a good taste of what type of questions that they ask on the AP test for this. Now, in terms of homework, I didn't make a slide, so let's write out what you need to do. You have your homework sheet, okay? You need to send me an email again. It is homework points. They will go in the computer. You do not want to lose them, okay? Email me. Tell me something you learned. You guys should be getting used to this. Any questions that you have? And what will we do for our last one? Tell me your favorite movie and why it is your favorite movie. All right, and I will chat with you tomorrow. Peace.